Let's see who is missing here. 2, 4. I expect 9, but 2 are missing. 3 are missing. Oh, Jusung is coming. Right. Okay, I'm in the process to really review the grading, the midterm exam. The winner for this midterm exam is Youngbin. Youngbin did really well. The problem set I feel was too easy. So maybe I'll make it a little more difficult in the final. But Youngbin, you did right for the difficult problem, but you did wrong for a simple problem. But anyway, you are the winner. And I want to wait for, did you see Seungwon and Youngwon? You didn't see in the office? They didn't come? Okay. Okay, today we're going to start chapter 4. As you look at my lecture notes, that's kind of the compact lecture note. So whenever try to understand the depth of the problem, then I want you to consult with Bandet's and PSO book that Pigu has it. In the exam problem, again, this year, I made one mistake in problem number 5. I give you the formula to make your life easy, and we indicate where the mistake was there. When I returned your solution set on Friday morning, then we indicated where that mistake in the formula is. It's problem number 5. So it's my fault. So that means if you solve the problem correctly, up to the point that you are using it to simplify the final solution, that's okay. Okay, there's no point to deduct it, things like that. Okay, before we start chapter 4, chapter 4 is chapter 4. Excitation and response problem. So we're gonna talk about the excitation and response, which is really input excitation and output response. So input and output response, we're going to deal first the single input and single output problem, but we're going to extend easily from single to multiple response. So once you learn the single input and single output problem, then others is much easier to solve. So for example, I have like a plate, whatever the figure, really doesn't matter. Then I attach the shaker here. I attach the shaker. Then I attach here the transducer. So transducers, in my note, if you look at it, that summation sign, that's the transducer. They have all different type of the transducer, depend on the measurement of the the frequency range. Okay, so then this is like what? This is input excitation. Shaker, it shake the plate. Then, of course, the wave will propagate in all directions. Then this is a pickup station. This is output. This is a pickup station. So this is output. It has a path. It has a path that wave propagate from one point to the other. So usually in the shaker, you have a gauge right out there. So here is a load cell. Then this can be screwed right in. Typical case. Changwon, where is Yongwon today? You didn't see? Okay. Screw type, then it measure the force right here. Transducer, force transducer is right there. Or this is just you can install the shaker by itself. Then you can put the pickup transducer. Usually is accelerometer. Okay, usually accelerometer. This is same kind you can install. Once you put the input transducer or shaker, you have output transducer. It pick up the wave. Then it determines the path. So then you will find the H tau or HF. What is it? What are these? Jongwon, what do you call small h and capital H? We learn in chapter 1. What do you call small h? 주성? Impulse, unit impulse response function. So this is like a unit impulse response function. And what about the capital H? Choro, what do you call capital H? Gusto, what do you call the capital H? Gusto, what do you call H? Exam is over now? No problem. Yunso, what do you call capital H? This was within the scope of the midterm. It's called the frequency response function. You heard about it? Yeah, frequency response function. I'm just giving you first the path, the direction I'm going to talk about it. Frequency response function. Another pretty common name is transfer function. You heard about the transfer function. It's called the transfer function. Same. Transfer function usually unknown. But when you installed the input transducer or shaker, then output transducer, which can be both the device to measure the acceleration, then that's about it. Then you can determine, you can find the expression for h, then you can find the expression for small h. Small h is time domain function, capital H is frequency domain function, which is called what? Which is called h tau and capital HF. This is called transform what? Pair. We have a Fourier transform pair for the spectrums, for example. Okay. And it's called the Fourier transform pair. So this is the usually unknown. That's what you needed to find all that. For single degree of freedom ideal system, of course, expression for H with no damping and dampings are pretty well known. And I gave you the chapter 4 for my vibration note. If you look at few page, the vibration notes, I think at the beginning of the spring semester I gave you, you should have. If you look at chapter 4, about the first 2 page, then there is a unit impulse response, then derivation, then you see the derivation for h, small h, then Fourier transform of h is the frequency response functions. Okay. So once then, when you measure it, this is a pickup station. We will go through the measurement, something like SXX. This is the power spectral density function. You can measure this directly using FFT. Of course, this is proportional to like e to the xt, not t, e to the like x conjugate to xf. Don't confuse this star. The star we use for what? Conjugate, right? We use for conjugate. Here is we use a conjugate. But I'm going to use this star with other meaning. We use, this case is of course, this is a conjugate. Simply conjugate, G-A-T. Simply speaking, change J to minus J. But another meaning I'm going to use today, right away, is another meaning. Now this meaning for this is a conjugate. Convolve. For example, X star Y it reads like this. X convolve to Y. Okay, that's another meaning I'm going to use it. And I'm going to giving you the lecture from the convolution theorem. This will generate the convolution theorem. Convolution theorem, some details of derivation is in the internet. When you type in convolution theorem, then you can see a whole bunch out there. But usually what I'm using is, you know this one, Wikipedia. PDIA or PDA. Wikipedia, you access sometime? Yunsuk, you heard? So if you're going to Wikipedia, you can get lots of information. So this is a simple roadmap. Chapter 4 is somewhat difficult for derivation. What that means is, if you just look at it, I'm 100% sure you will screw up. I want you to, as you follow my lecture, I want you to really write it down yourself. X and tau for some equation has a different meaning. So it's better each equation set take a deep taste. What does it do? Of course, I'll explain as much as I know. Okay? So chapter 4 is you need a little bit thought and write it down, the equation. That doesn't mean that to memorize it, no. But you should. So this page is a kind of independent to chapter 4, but you need this. Convolution theorem is what you need before we going into the chapter 4 and digest all the equations that I put that in. But the relation, all the relations I have derivations on Sxy, Sxx, and using the input excitation. The thing is to get the output solution using the input excitation and the path information. This path information means the h, small h, and capital H. Okay? So that's what we're going to do. And we all know that. What's this? This is a Fourier transform of xt called capital X. I don't know how many times I wrote that. Quite a few times from the beginning of the class. So this is the beginning of chapter 4, but before I talk about the inside story. So theoretically, this is minus infinity to mathematically minus infinity to the infinity. Then of course xt e to the minus 2j, see I missed it, 2 pi ft dt. And this could be related to like input excitation, for example. and YF similar YT e to the minus j 2 pi ft dt. Shown right here. Be careful, if I make mistake, you have to point out right away, otherwise I'll just go wrong direction all the way through. Then this is convolution, the part here, x convolved to y. So this is the integration of x tau y t minus tau d tau. You saw this where? When you took the vibration class, this is the first equation. This is replace, well, I'll write it down, the equation, then you will see that in a minute. Okay? So convolved xt convolved, not the conjugate, yt is equal to integration minus infinity to infinity x tau y t minus tau, right? D tau d tau. X convolved to y. Simply, this case is simply notation. So notation, by using the notation, you can eliminate the all others. Then the convolution theorem states that this is in the time domain, going into the frequency domain, then its convolution goes to the multiplication. Convolution in one domain is the multiplication in other domain. Convolution in time domain becomes the multiplication in the frequency domain. This is kind of the convolution theorem. So this is Fourier transform. Fourier transform of the convolution of x and y become the multiplication in the frequency domain. One domain and other domain. So if I can write this, I use ft, sometimes I use like this, which is same as a Fourier transform. Fourier transform of x convolved to y is equal to x. This case is a function of the f, then multiplication of the y. So here is convolved. It's a Fourier transform of x convolved to y is equal to multiplication in other domain. So that's what you have to really remember. I use sometimes ft is a Fourier transform of this guy, is multiplication of the other. So in general, what I can write here is this. So, of course, if you take inverse Fourier transform, then you can get the multiplication part. Before I write this, I would write this. Fourier transform of x. This is a time domain function. This is t. This guy, the y, is a Fourier transform of x multiplication of Fourier transform of y. Simply, I use this guy as xf multiplication yf. Very straightforward, but sometimes it's confusing. So now, that's the theorem. Now, I'm going to write like this. Fourier transform of x. When you make a Fourier transform, you do in engineering time domain function. Multiplication of y t. This is a really general expression. Fourier transform of x. I'm going to use a bracket or this. Really doesn't matter. So, this is still part of the convolution theorem. And of course, if you look at from here, then I can say x can drop the t and f, y is inverse Fourier transform of the those one is minus 1. You can read this. I hope this is Fourier transform, which is a Fourier transform, inverse Fourier transform of x dot y. Just remember, when you take a Fourier transform of one domain, when you do that, going into, in our case, is a frequency domain, which goes as a multiplication in that domain, which is a part of the convolution theorem. So just a continuation for this, giving you a little bit the different set. So this is that. So from here, if you take the inverse Fourier transform of this guy, so inverse Fourier transform, so which is minus infinity to infinity, so x dot y inverse Fourier transform j 2 pi f tau d what? df becomes, of course, nothing to confuse, sometimes confusing. So that part you have to do. So I got that. So this is very general expression. That's about all. when you go from one domain to the other, then convolution switches to the multiplications. Okay? So now we can do chapter 4, beginning of chapter 4. But before getting into chapter 4, we're going to look at this part. Okay? So this is a system. This is a system like a plate, any complex structure system. You put the two transducer or one shaker and one transducer. You can put the excitation relevant transfer right down here. You can put another transducer to pick up the output. Then input, output, excitation, response. Then whole system, using the whole system, you can really get the system path, the H or capital H here. So this is output is a Y. This is input, and H and capital H is telling you the system expression, transfer function, simply speaking. So Y is equal to XT convolved H. Have you seen this before? Where did you see? Chapter 1. If you look at this is what you see, chapter 1. And in the chapter 1, Y is equal to XT convolved to, in this case is simply the HT, and the next expression, XT still carries as is. I can put inside the integration, because integration parameter I use is a tau. So this is really, this is tau H T minus tau d tau. And for this, for the single degree of freedom system, let's say no damping, this is equal to 1 over omega n sine what? I forgot. Some sine omega n t, which is like this. Where do you find this? Chapter 4 in vibration lecture note, I put it down. It's sine omega n t, right? Yeah. And this, I ask you sometime to prove the equivalency, which is equal to minus infinity to, general expression is minus infinity to cover the whole time domain length. So H tau x t minus tau d tau. Equivalency. Where did you find, where do you get the proof? which is in chapter 4, the vibration lecture note. Right down there, you will see that. Right at the middle, just replace like this guy. You see, I replace that guy as a T1 and manipulate a little bit, then you will get that expressions. Vice versa. This is right here. Right? This is a time domain, then this is a frequency domain. So it really goes up. Sorry, but the capital Y, we are using the output response in time domain is equal to F, or I use Ft of Yt. And Y is a convolution, so Ft, so convolved, X convolved to H, right there. Then when you take a Fourier transform, this is in the time domain, the convolution goes to the multiplication, time domain and frequency domain. You see? So here becomes the X, which is of course a frequency domain, is multiplication, and H, or this multiplication is commutative. You can change the order. So you can change this guy as H, Y. A lot of times I will start to drop the F, or F comma capital T. I will start to drop that, because we all know that there's a function. This case is a function of, let's write still few more lines to carry over. X, which is telling the first story. So Y, F is equal to H, F is simple multiplication of X, F. This is nothing new. This is really, you saw that in chapter 3 and part of chapter 1. Nothing new. And we know for the spectra via Fourier transforms. So S, I use SYY. Stuff is, for example, F S of SYY is equal to, I said something okay, how can I explain this? This is a limit. T goes to infinity, 1 over T, and I think it's e to the xf careful. This is what? Conjugate, careful, okay? That's a conjugate. I warned you from the beginning. That's not the convolved. So that's why I mentioned this spectra is proportional to e to the x f. In this case is like this. This is equal to, can I do this? Can I do this? Right, this conjugate is like x real plus j x imaginary, x real plus j, and you have to put minus. I'm gonna write like x real minus j. I should write like this. Minus. Because it's a conjugate. This guy is xr plus the j x imaginary. Then this becomes xr square minus, then j square is minus, is a plus, xr square and plus xi square, something like this, which becomes something like this, xr square plus xi square, and you can say bar as absolute or just a bracket times square. Pretty good. So this is proportional to this guy. So now I can say this guy, this becomes, I'm just showing this guy is like this. So that portion becomes SYY. I can say that becomes, I can write, anyway, becomes first x is h conjugate. I can say x oh, this is I made a mistake here. What's a mistake here? This should be, if I put the x here, this should be xx. So be careful. You can screw up very easily here. So that's SX, correct? Yeah. When you introduce h here to the x, then that becomes the y here. This is also, I can say y, this is simply y, isn't it? I'm trying to get the relationship SYY is equal to H star SXX. That's what I'm trying to get that. And this is what I want to try to get that. This becomes that. Then, got it, then you are not going to confuse it, but why? I just rewrite right here. y is equal to h y, I'm sorry, h x, and I'm going to write y star. Then I have to write one of this guy. I'm going to do it here. H star x. Or I can simply write this, that. No differences at all. I'm going to rewrite this guy as H star conjugate H x star. Is it correct? You tell me. So this is proportional to proportional divided by 1 over tau. Set the limit t goes to infinity. This becomes SYY. And now this guy will become SXX. So you can say that SYY is equal to H star H SXX. So this guy is H star SXX. All this manipulation is very important. Usually you can measure SXX from the measurement. You put the transducer, then you can get directly SXX. Okay? Then SYY you can measure too. Then you can determine this H square. H square, you can determine the magnitude only, no phasing. And SYY is auto or power output spectra. You don't get the phase information. You see, you can't go back. So here is SXX. This is, of course, frequency domain function. And this guy is, of course, frequency domain function. Oops. Using this with the non-measurement, you can determine H square, not the H, that's what I'm saying here. Then next you have to determine the SXY, which happen to be, as I wrote, not here, is going to be, as we will prove, is important. How do you do that? Using the XY expression. From now on, it's very similar, but still confusing. So, Y is this. So, what you can do? You can you can multiply the capital X is multiplication. Okay, if you do that, this will become, they take the average, e to this guy, multiply 1 over t, take the limit t goes to infinity, then that goes, you can express in this form, x carries over as is. Simply multiply, you multiply right here, and h, f, multiply, is all commutative. So I can say that, which is h, f, x square which is, for this one, you can take the mean e to the divided by 1 over, multiply 1 over t, then take the limit, then this will become sxx. So one additional equation is this. Measured, then you can determine the h function, frequency response function. That's what you need. It has a magnitude and the phase information. Using power spectra, you will determine only the magnitude. I'll stop right here today. So this page is one page, but lots of information. You can see it. This particular page. So we'll continue from Friday. It will be much easier, then a little bit confusing, then stabilize it, then we'll move on. Okay? Any questions? Don't confuse. So review this after you return, then it's going to be all okay. Okay, I'll see you then Friday.